Hello, my name is Robert Smith, and I'm with New River Community College. And today we're looking at techniques to identify Lewis acids and bases. And I have two examples here. And we start off with the one where we have boron trifluoride reacting with ammonia. So when you're looking to identify which one is the Lewis acid and which one's the Lewis base, I find the best way is to simply draw the Lewis structures. So for boron trifluoride, we would have this as our Lewis structure, trigonal planar. But and I just know this from having done it so often, but if you want to practice it, you would again start with boron in the center and then put fluoride ions on, or fluorines on each of the sides, and you would draw a bond to each of them and then start filling in an electron lone pairs until you have the correct amount of electrons, and then if you had excess, you'd put it on the central atom. But for this case, we don't have any excess. Um, and the other species is ammonia. This has a pyramidal structure, so we know that it has this lone pair up top. So what you would want to do is take a look and see who has their octet filled first and foremost. We know that ammonia does. It has, for each bond counts as 2 electrons. So that's 6 electrons from the bonding with hydrogen. And then it has a lone pair up top. It has just 2 electrons. So that's a total of 8. Boron has 6. It has 2 from bonding from each fluorine. So it's actually has an incomplete octet, which makes it it's a sp2 hybridized boron, and it is susceptible to accepting of electrons because it has an incomplete octet. It's electron deficient. So that would simply mean that because the boron can accept electrons and the nitrogen can donate electrons, that would make the boron trifluoride a Lewis acid and the ammonia a Lewis base. That's a fairly simple example. Slightly more complicated, but also not, I mean, none of these are very complicated if you actually draw out the Lewis structure, would be the reaction between water and carbon dioxide. So for water, you have oxygen and has 2 hydrogens and 2 sets of lone pairs on it. And it's going to react with carbon dioxide, which, again, if you draw the Lewis structure for carbon dioxide, you get this. Now, this one's a little different. They all have a complete octet, so it's just a matter of looking at how this reaction would work readily. The result is carbonic acid, so let's see what you would typically do. So typically what would happen is the nucleophile would attack the electrophile or the electron deficient species. And in this case, you're looking at a more electronegative species attacking a more electropositive species. So, and this is kind of almost an intro to organic chemistry in a way, because these are the kinds of things that you would do in organic chemistry. So the electrons on the oxygen would tend to want to be accepted by the carbon, which, because that would push up the number of electrons to beyond the octet for the carbon, that forces one of these double bonds to break and jump up here. You end up with this H2O bonded with a carbon, singly bonded with an oxygen, and doubly bonded with another oxygen. And you can put those there, and there should be total of 6 up here, and this one should have a positive charge. And then what you have is what's called a hydride shift, where one of the hydrogens on H2O jumps up to this negatively charged oxygen. So you end up with, actually, I'll draw that up here just because I have a little more room. What you end up with is carbonic acid. You end up with that. Okay. So again, in identifying Lewis acids and bases, the Lewis acid in this case, in the second case, was in all cases are the electron acceptors. So in case 1, it's the boron trifluoride, and in case 2, it's the carbon dioxide. And the Lewis base is the electron donor. So case 1, it's ammonia, and in case 2, it's water is the Lewis base. And that's all you have to do. You just have to figure out how best to display your species as in Lewis structures. And then if it's electron deficient, you know that that's going to be your Lewis acid definitively, as was the case with boron trifluoride. If there are no electron deficiencies, you have to see which species could accept electrons without there being too much of a rearrangement. For example, if you tried to make it so that carbon was donating electrons to this oxygen on water, then you'd have to break off a hydrogen, and that wouldn't make much sense in terms of now you have a free floating hydrogen, and there's no way to definitively say where it will go. So in order to make this final product, you have to have the oxygen attack the carbon. So the water has to be your Lewis base, and carbon dioxide has to be your Lewis acid. Okay. Thank you so much. You have a great day.